not silicon. 30 seconds to light. It's 11 o'clock on the fifth Sunday morning of the month, which means it's time for a special chai and wine session up close with science, where we take you inside a lab at the TIFR. As you can see, we are inside a clean room, all dressed up, smoked up, so that we can be here. And we are in the silicon detector lab of the Department of High Energy Physics at the TIFR. I'm sure you all know about silicon. It's the material that drives our world today, laptops, cell phones, whatever you call it, all our electronics is based mostly on silicon. But silicon is used for a lot of other things. You can make detectors out of silicon. And probably you certainly know one of them, which is a solar cell. A solar cell absorbs light, it detects light, generates a current. Similar to that, there are many different kinds of silicon detectors, and in particular, you can use silicon also to detect particles, tiny particles. By the way, a silicon wafer is basically something like this, on which different circuits have been made. You see these little strips, these are strip detectors, and this is what this lab works on. This is what the session is going to be about. And to tell you about that, we have people with us. First, we have Kamesh. Kamesh is a senior scientific staff member in the lab who has been at the TIFR for more than 25 years and is basically the person who runs this whole facility over here to make sure everything works. By the way, these detectors that we make here actually get used in international experiments. For example, international particle physics experiments at CERN in Geneva or at Bell in Japan. And guess what? This lab, the PI, Professor Gagan Mohanty, is at CERN right now, and he is going to join us live from CERN. Can we just spotlight Gagan's video? So we can spotlight Gagan. Hi, Gagan. I hope you're there at CERN with us. Can you just say hi to us? Let's see. Yes. Spotlight your video.
I hope you can hear me well.
We have Gagan there. So Gagan's going to be joining us from CERN. Yes, Gagan, can you just maybe tell us a few words about yourself before I introduce the others over here?
Yes, good morning, very good morning. And it's very early here, 7:30. So instead of having real chai, I thought, why not I join virtual chai and why? Yes, so I'm here at CERN. This is the lab where this very famous Higgs particle, also known as the God's particle, was discovered in 2012. And silicon detector played a very crucial role. And of course, we will discuss that more. So I'll come back at the end in case there are some questions and something to be discussed. So right now I will sort of go back to take you back to my colleagues in Mumbai. So.
Okay, thanks, Gagan. That's great. We will sort of get to the part of the show where you can tell us a little bit more. Of course, remember, in any lab, the hard work is done by students. So let me introduce the two students who are with us today. Who are going to be telling us about the work over here. So first we have Mukund Shelake. Mukund, hi, just tell them what you do. You are in your which year and things like this. You can just give a 30-second introduction.
So hello, I'm Mukund. I am in fourth year of my PhD here at High Energy Department, and I work basically in the CMS collaboration for my PhD towards in the partner that COVID.
Great. Along with Mukund, we have Lokesh. Go ahead and introduce yourself.
Hello everyone, I'm Lokesh Bhatt and I am third year PhD student here. So currently I am also working in the CMS collaboration, and right now our silicon detector lab is doing the module assembly work. So I am also involved in this.
So in case you missed it, CMS is the compact muon solenoid. It's one of the big experiments at CERN. Okay. So with that, over to you, Kamesh. Lokesh, Mukund, you guys are going to take over and I will monitor it. Audience, please remember, we cannot see you. The only way we can deal with your questions and answers is on chat. So please remember to put your questions, comments, feedback, whatever on the chat, and we will take it up. So look at it, inform these people, and we will then answer the questions for you. So please put your questions and comments on the chat. Okay, over to you.
Hello, good morning, everybody. Before going to the detector part, initially Mukund will introduce about the particle physics. What we are going to say is the silicon detectors of particle physics. So Mukund will introduce about the particle physics. After that, I will come to the detector part. So Mukund, can you take care of that one?
Yeah. I will start sharing. Okay. Hello, everyone. I will give a brief introduction into particle physics. So basically, why we have to detect particles. Share.
Okay, good.
So first, we will start with the atomic model. We all know from our school days that all the materials are basically made up of atoms, and each atom consists of proton, neutrons, and electrons. Proton and neutron being in the center at the nucleus, and electrons revolving around them. So this is basically the atomic model that we study in school. But what we do at the high energy physics department here is about the more fundamental processes or more fundamental particles than the atomic model. So when we probe deeper into this proton, neutron, and electron, we figured out that proton themselves are not fundamental particles. Here, by fundamental particles, I mean the particles that are not divisible into further smaller particles. And so we, in the last century, we have figured out that the proton itself is made up of three quarks, basically two u quarks and one d quarks. Similarly, neutrons are made up of one u quark and two d quarks. So these quarks themselves are fundamental. They are not further divided into something else. And electrons are fundamental on itself. So similar to this u quark, d quark, and electrons, we have figured out the complete set of fundamental particles that we know of as of now. And this is called the standard model of particle physics. It consists of quarks, leptons, some gauge bosons, and famously known as a God particle, the Higgs boson. And so our study here, or what we want to detect in the silicon detector experiments, are these particles. And generally the study is done in large or big collider experiments, similar to ones we have I'm showing in this slide, the Bell experiment and the LSC experiment. So Bell is in Japan, LSC in Switzerland. So roughly their modus operandi is they have two beams of particles, one coming from one direction and another in the collision direction itself. And then when these beams of particle collide, many particles are generated. And these particles, as you can see in here, the black traces of these particles, the detectors are used to detect these particles. And we will go now into the detector part of the tour and figure out how these particles are detected.
So let me ask you a question. So when you said particles are being collided, does it mean that you are colliding these elementary particles like the quarks and things like this, or are you colliding maybe protons or electrons or other particles, and when they collide, new particles get formed, and those are what you detect?
Yes.
So basically, it depends upon the experiment. So in case of Bell experiment, we collide electron and positrons. So basically, the fundamental particles. But in LSC, we collide the two proton beams. And these proton beams are consist of like billions of protons in each beam. And so at the interaction level, we say that the interaction happened between the quarks inside these protons, and each such collision gives out many different particles, and we detect them at the detectors. So this was about the collider part of the experiments. Now the detector part of the experiment and how the silicon comes into play. Go into Kameshwar's presentation.
Yeah. So just now we have seen the detector. Now I will tell you how this detector will be manufactured. So normally this detector is nothing but a simple PN junction diode. So we will be particularly silicon will be doped with the boron to become a P type, and to become silicon will be doped with the phosphorus to become that type. These two will be combined to make the PN junction diode. Normally for this detector we always use the reverse bias. Why I will use the reverse bias? What is the principle of this thing? I will tell you this one. So here you can see the detector. Particularly, what we will do here in this thing, sir, we'll take the N-type wafer, and on that thing, what we will do the P-type implantation will be done. So depending upon the size, I will show the size, what is the length of this thing and width of these things. I will tell you which is major importance for the spatial resolution. For the purpose of this detector, when particularly bell 2 used to mean the spatial resolution of the track to track the charge particle. That's one thing. So this P implantation will be done. After that, we'll put the oxide layer to make the capacity coupling. So readout electronics. I have a little bit pictorial representation of each layer. I will show in one of these things. But particularly in this type of things, two types of types are there: N-type bulk and P-type bulk. Particularly N-type wafer and on the P implantation, that's mostly used in detectors. And depending upon the application, also sometimes they will use the P-type also. Okay. And whatever I showed is the earlier one is the single sided, because the wafer is there, what the strips are only the one sided. So because of that thing, only we can measure the one direction, either X or Y, whatever the way direction. But the what we need is particularly all these detectors, the near to collision point, the space is very limited. We need to get the maximum information from the detectors. So what is the preferable is I should get the two-dimensional coordinates of the charge, but that's why people will go for the double-sided silicon microstrip detectors. The double-sided silicon microstrip detector is nothing that one side is the X direction will be there, the other side of the detector, the perpendicular to that one, perpendicular to that one, the another strips will be there. These two are perpendicular to each other. This way we can detect the two-dimensional coordinates. But the process of this thing very complex. Only few companies in the world they can process this type of detectors. And some of the picture here you can show the same thing which you have done here. How the internal structure will be there. He can shown here, and particularly in the double sided, the issue is there. Particularly the other side, particularly the N side, the electrons will be accumulated. Okay, so to avoid that thing, what they will do, there is a separate p-stop structure they will prepare, so that to isolate the electrons which will become a short, so they will isolate with this thing, particularly this double-sided detector. This setup will be there. And particularly, as I told you, this is to measure the tracking as well as the energy. So here you can show is the once you know this where is the in the X-ray position, where you will be showing that where the particle is passing to these things. So whether they depends upon the energy deposited and the signal collected from the strip, we can make out that whether the particle has spotted to that structure, that coordinate that strip or not, we can count out. Similarly, it will give the energy or the charge of the particle, how much is the charge it deposited into this thing, also it will create into that one. And not only one this thing, whatever I showed is the only one type, but we need to track it, the particle. We need to track it. So what we'll do, instead of one layer, we'll put the number of layers. Particularly what I will show you later, the bell 2, we have been using the 4 layers for the silicon detectors. So this way we can track the particle into that one. Okay. And not only that thing, yeah.
So maybe let me just interrupt you once. Let's make sure we've understood what is happening. So what we have is basically a diode, which is something made of p-type and n-type silicon. It's a diode. We put reverse bias on it, which means the p-type is connected to the negative voltage, the n-type is connected to a positive voltage. And when a particle hits this, it will generate a signal. Now we want to know, what do we want to know? We want to know the energy of the particle and we want to know where the particle hits. So what they do is, on top, there is a series of strips this way. Okay, let's say this is in one direction. And on the other side of the wafer is a series of strips in the other directions this way. So this is on both sides of your wafer. So depending on where the particle comes, you know exactly at which strip X, let's say one of them is X, the other one is Y, we know where it hits. And if you have multiple such detectors, you know it hit this one here, the next one there, the next one there, the next one there. Then you can figure out the track of the particle. Is that correct?
Exactly.
Okay.
So in this thing, to add to these things, what we'll do once you reverse bias it, what will happen to the detector? So whenever the charge particle goes, it's the inside the electron hole space will be generated because of the ionization. So this is the particles these charge particles we need to collect at the strips to get this signal. That's what I showed in the next slides, the charge and everything. Yeah.
So are these the strips that we are seeing here?
Can we stop this slide share for a moment?
Yeah, can you stop the slide share? Just stop share. Yeah. So are these the strips we are seeing?
Yes.
These are the strips?
Yes. Yes.
Right? These are the strips.
So yeah, this is what I am showing. What we are showing is the prototype. So what our strip width and pitch become a very important for us. Particularly the pitch gives the spatial resolution,
which means the separation between the strips.
Two strips.
Okay.
Yeah, separated. The center of the one strip to the center of the another strip, that is called pitch. So normally pitch divided by root 12. This is the formula we use to calculate the spatial resolution of the charge particles. So here is a prototype. We have kept the different sets are there. We have 11 sets are there. Each have the different width and pitch. This is for the prototype. So we for our study purpose, we made different steps in this thing. And particularly, this is what we have done is on a 4-inch wafer. And this particularly the preparation of making of this thing was done by Bharat Electronics Limited, because we need the good fab to handle this type of wafers in a big wafer. So the handling of this big wafers and to be big there, it is like a very big to having almost all. This is a 7.4 centimeters here, and this is and what the total area, that particularly strips, that is the length we have. So, and the width, whatever you have, the different widths, and roughly whatever our purpose will use sometimes we'll use the 50 micron is the width and 70 micron is the pitch. That's what one of the detectors will use out this.
Then start this. Can we move it?
Can you see?
Yeah. Yeah, we can see the.
Yeah. So now we understood what's happening in our detector, and now to make this detector, particularly we need a fab. As I told you, we had done in the fab. So what we'll do is that in the fab, we have to make the mask for this type of design. It's not a straightforward. Just putting p-type and n-type and combining these two doesn't make it makes a diode, but for our purpose, we need to have so many things in the, we have to make the mask such a way that to make a perfect detector for ours. So what we'll do is that on the, as I showed you, where we are using the 4-inch wafer, the circular wafers, that is n-type. On that thing, first what we'll do the p plus implantation. These are the strips. P plus implantation. That's what you can see here. P plus was the first layer. Here, this all green line. Green is the P plus implantation, and on that thing, we'll do the oxide ion on the top of that one. And after that, we need the contact opening for the polyresistor. I will tell you what is the purpose of the polyresistor. And after that, we use the resistor here. For biasing of the purpose, we use this resistor here. And this is the metallization on the AC pad and DC pad here, and this thing. And this is the metal layer, one more metal layer, because on the top, that's where we'll take the connection for that thing. And above that thing, we'll make the protective layer. So once this is so many layers, we have to do it one by one, and for each and everything, no contamination, anything. So during this process, if you do any contamination which we are unable to detect those things unless you go to the crystal level, so my characteristics of these things will doesn't give proper results. So which will then these you cannot make in immediately. It's like a simple device. It takes a lot of time to preparation, making, and everything. So everything should be perfect. And particularly, this is a detector which is shown here, and this is one corner. We'll try to show this is under microscope, which you can see here. Use the mouse because otherwise it can't be seen on. Yeah. So these are the one corner I am showing here, and all these things as process. This is one corner I am showing here. So this is called the bias pad and the DC pad and AC pad. What we'll do is that what we'll do is this is a bias pad. So we'll apply the reverse voltage between this pad and the back side of the sensor. So this is the these two PN. So the voltage we apply, reverse voltage will apply. That's one thing. And we'll do all the tests of these things on this detector. And these are the readout pads, the DC pad and AC pad. Normally, I will take the signal from the AC pad. And particularly, this is what all these things, the connections. I will tell you the connections of these things. Connection to readout electronics. We have to perform the wire bonding because all my pads are in micron level. Okay. So the pad is around 50 by 250. So in that thing, you make a connection with the readout electronics, readout chips. And particularly these are very sensitive. So we need to be readout to be as close as possible to the sensor.
You said 50 by 250, you mean microns, which means it's 250 microns is 0.25 millimeter. Remember your scale, millimeter division. So a quarter of that is a big size and 0.05 millimeter is the other size. And you have to put a wire on that. And you need a special thing called a wire bonder for it. And that's what they do. Can we see this under the microscope? Later. We'll finish this.
Just 1 minute. I have something is there. Yeah. So one more is there. After that, I will. Okay. You can see that thing will come to the characters.
Whatever. Remember that if you want to show something, we have to stop share and then we can show.
Okay. Then we'll show it. Then we'll come back.
So let's see this. Let's see this. So what we'll do is we stop share. And of course, remember that once you stop share, I mean, this was our wafer. And what we're going to do is we're going to see under the microscope what is there at one of these little corners of the wafer. Okay. So we have here a microscope.
So normally this is the way we'll look into this thing. Okay. So now we'll try to show it is possible to.
So basically, first maybe you should show them the wafer under the microscope. That's the wafer under the microscope. You can see the spot of light. The spot of light is where the microscope is being focused. And let us see if we can somehow get this to you. You got to align your camera with the microscope. There we are. And you can adjust the brightness. Okay, good. Where's the light? You see just the light brightness? No. I thought, or is it focus is this, right? Okay, you hold it. I can do this. Okay, I'll tell you what. We'll look at this. We'll figure out how the microscope focus for the mobile, and we'll do this. Meanwhile, you can go on to the other thing. I'll figure it.
Actually, I think you have an image to be shown that, right? Over to you.
Yeah, we have.
That's
I'll figure this out.
Share. So once that my detector is ready, what we need to check whether the qualities are good or bad. So you have so many things, measurements will there that what we call the characterization of the silicon microscope detector. So the standard one is the IV. So what we'll do is what is the purpose of IV is that we will apply the voltage and measure the current. It's a reverse pass. So as you know, so in these things, what we will get the reverse breakdown voltage will find the breakdown voltage. Normally, for any detector, the breakdown should be as large as possible. So, particularly, if I have the breakdown voltage for 800 or 1000, it's very good. The reason is that I will tell you later. Why and this thing, another is that the bulk capacitance. So the CD, what we call it. The CD is also the bulk capacitance by applying the voltage and measuring the capacitance. This is the capacitance which gives the depletion resistor capacitance. So once you deplete it, it will become a parallel plate capacitance. So then that's part that is a area which we are interested in, the charge particles and the other things will be there. So from these things we will come to from there's a plot will be there. Once you plot it the CD, you will get the operating voltage of this in such a way that we will deplete all the charged part here. Whatever the electrons goes in that depletion region should be separated out. So we'll apply the voltage of the operating voltage, operating voltage, called depletion voltage. Operating voltage will set it, and that voltage will be over depleted a little bit. Suppose if it is a 30 volts or 40 volts, will over deplete, so that there are no more charge carriers within that. So over deplete. That is the reason we will. Other than this thing, we have all these things is there. Each strip capacitance and interstrip capacitance, and this is the resistor is there. The resistor, what's the value of this resistor? Everything will measure it with these things and in the direct other things.
I will join the Zoom call for this.
Yeah. So this thing is one of the picture I'm showing is the characteristics. This is IV, so it shows that we are keep on keep on increasing voltage. Of course, I am putting in the first quadrant. Don't worry, this is the reverse bias. Only for this is standard procedure. People will show. That's what I am showing the same thing. So we'll keep on increasing the voltage in steps of 10 and try to measure the current. So this is the what plots comes after certain time. Voltage comes here. The current starts increasing. So I kept at my limit at the 50 microamps. So this is the instrument has this capability, so that once it reaches 50 micron ampere, it stops applying the voltage. It will safeguard my detector. That is a good quality of the instrument. Yeah. So this thing, after this thing, I will show my probe station, how I will probe with the detector to measure these things. So two things are there to add these things. One is the probe station to probe my sensor as well as my instruments and the desktop. So these instruments and the desktop are connected with the GPIO cable, and right now I am using the source meter unit, which applies the voltage and measure the current, and which I am capturing this signal to
the slide. Then we can show the instruments.
Yeah. So now I will show my probe station. This is the manual probe station because this is what we have and we will see. So here, right now, this is called the step on that thing. The sensor is placed. This thing, what will be vacuum check, because while putting a probe on that thing, it will move. So we should not move. So that's what we will do is. Yeah. So we hold with the vacuum. We hold with the vacuum, and through microscope, I will adjust the probe. This is XYZ stage is there. The probe tip is there. So the probe is the 5 micron. So that thing will place on the detector as the bias pad or AC pad, depending upon these things. Okay. And the backside connection we are taken from the bottom. This is the end.
So what you are doing is the wafer is held with vacuum.
Correct.
And then under the microscope, you put the leads on the sensor at the desired place. Is that correct?
Correct. And this wire is connected to the instrument. So these two wires are connected to the instrument. So these things, whatever the voltage and everything, will apply it here.
And so why the environment is dark? Why?
Yes. So normally we are measuring in microamps. Sometimes it goes to nanoamps also, because even the strips current is very, very less. So normally what you do to add any current coming from particularly these light also introduce some current to this thing to avoid this leakage current to be added to the environmental leakage current added to the detector. Will close these things from all the environment and we'll try to measure that.
So is this electrostatically shielded?
Not electrostatically. It's only the light. Only light. Yeah. So because with the light you can see the increase in the leakage current. Yeah.
Okay,
Yes.
Next video. You'll have to go there and spotlight my video. So you have to share the screen, right? No, I don't have to share the screen. It's just the video, right? So it's my video. Yeah. So there we are. So this is under the microscope now. What you're seeing is, oops, what did I do? I just killed my video. There we are. Oops, why did it go ahead? Okay.
Yeah.
So now you see it. And these are the strips. These are the strips of your strip detector. And at the end of it, if you are very careful, these are the pads that we will connect our thing to get the signal out. Okay. Yeah. Okay, you can switch back to the.
Share. Yeah. So right now, what I showed is the detector characterization in our lab. So
now you have the detector ready, and now you're going to tell us what experiment you are doing using the detector.
yeah. So these detectors, particularly, whatever we use here is a Bell 2 KEK vortex detector. It has the pixel and strip detectors. So this is the what we showed in this thing is that is a vertex detector. And
Please use the mouse because your finger can't be.
so no issue. And this vortex this is a Bell 2 detector. In the center of these things, particularly near to interaction point, most of these things are silicon pixel and silicon strip detectors will be there. And here, whatever we call is a vortex detectors. It has consisting of 2 layers of pixel and 4 layers of double-sided silicon strip detector layers will be there, which you can analyze. You can see here. This is the picture of the SVD, which you can see here. I will give more description of that one here. And here the ladder layout. So this near to interaction point, we have the particularly SVD. We have four layers are there: L3, L4, L5, L6. These fellow has double-sided sensors. Okay, and to get the two coordinates, two-dimensional coordinates, and these things are 4 layers are there, and from the interaction point, these are the distances from the interaction point. Particularly L3 is 38 mm, L4 80 mm, and L5 is 115, and these are the 140. And L4, if you see here, the L4 out of these 4 layers, we TIFR build one of the layers, that's the L4. And other layers are built by other people. And particularly the forward and backward, you have the forward and backward. This thing is assembled by the INF and PISA. And to assemble these things, what we need is a lot of work will be there. You cannot just make the assembly so easily. So I am listing out a lot of things. We need a clean room, and particularly precise placing of each instrument is very crucial for us. And we work in a particular placing of a few hundreds of microns is the tolerance they'll give to between the two sensors. Okay, and we need the mechanical fixtures, so we call the jigs. And to do that thing, we developed 3D models for that thing. After that, we converted to 2D, and we need to produce these jigs, and we test it, verify, and if anything you need to fine tune the jigs also. Once these things or jigs are ready, then what you need to do is that we need to use these jigs and do all the procedure. Particularly, these things are main important is the gluing. So, what is one part, and wire bonding, and that is the two. And after that, think about placing this thing as per the requirement. Particularly now, these things placing the detector at an angle of 11.9 degrees. That's what we around this thing. And after these things, we have to make sure that my ladder is working electrically. That's what, otherwise you cannot use it. So that's what we have done these things. And I'm just showing one of the picture of the 3D model and the one of the jig we produced here in the TIFR. We produced all these jigs in TIFR, and we are assemble these things. And to show these things a connection, particularly as the earlier told, that making the connection between the sensor and the readout. So what you need is the wire bonding. So this is what we can see. This is the readout chip. On these things, the few rows are there. So we need to perform the wire bonding between the pitch adapter. It's called the pitch adapter. This is the signal coming from the sensor. We need to perform the wire bonding here. That's what we have done here. And we have successfully produced the 10 ladders for the Bell 2, and here are successfully installed. So this is the full setup for all these ladders are installed into the KEK Japan.
So you were in Japan for this installation?
Yes, we should be part of the producing the ladders and testing and delivery at the KEK and installation. Also, everything was done that day. That is the detector part, particularly on the silicon detector part. Now we'll come to the HGCAL, high chromatic calorimeter. So what this existing LSC experiment, particularly, they wanted to upgrade to the next level. So because of that thing, once you upgrade it, a lot of things will be there, particularly the radiation effect will be there, and they will target for the luminosity also. These are the factors which I'm showing here. They are planning for the luminosity to be increased by 2.5 to double or thrice. Thrice they wanted to increase, and the radiation, because of the radiation also increases. To the detector should able to withstand this radiation and the luminosity. So for that thing, they have gone for the high granularity calorimeter. So what is this high granularity calorimeter? This is one of the layer I'm showing here. In one of these layers, you see one of the tiny tile I'm showing here. This tile consisting of the 4 components here, which I'm showing is here, which consisting the base plate. On that thing, the kapton will be placed. On that thing, we'll place the silicon. Silicon of this structure will be there, because here is a small structures will be there. These are small structure, and which is the small area of 1.12 centimeter square. This is the area roughly, and this area will be there, and each cell act as a device. And on the top is the PCB with radioed electronics. So what we will do, we will glue all these things with the gantry system, which will show you how this thing can be done. And after that thing, in this thing also, what is again the connection between the sensor and the PCB, we need to perform the wire bonding. So I'll show that thing also in this. So in these steps also, standard steps, base plate and the sensor, we need to glue it with the gluing robot. And right now we are using the gantry system for that thing. And after that thing, you can see the wire bonding, which again you can see here. So we need the only one wire bond is sufficient. For redundancy, we place another 2. So total 3 wire bonds for each module, each cell, I can say. And some of the testing, because full testing also will do it. So this is to optimize my bonding parameters. And after that, we need to study whether my module is here. Also, one more important thing is the physical distance, delta x, delta y rotation. These are also very important, and particularly our tolerance they have given is the delta x, delta y between 50 micron to 100 micron, and the rotation between the base plate or sensor distance is around 0.02 degree.
So you have to work under very tight tolerances.
Yes. We need to get the tight tolerances.
Okay.
Yeah. So the other part I will show. I try to done the setup. Okay. It should work. Then we'll go ahead.
So can we stop the section? And so we are going to some other instrument now.
Yes, actually this is mainly the characterization lab. So we prepared another lab mainly exclusively for HGCAL. So what is that? I will show some of the instruments for the HGCAL module, and we have a big gantry. So it's a robotic unit which will use to pick up and place. There also we develop a lot of jigs fixtures to pick up and place each component safely, and we need to perform the gluing and wire bonding also. These are the two basic important instruments I will show in the next lab. Please come.
You go.
Okay.
Yeah.
So I will introduce my instruments, then I will show you what each instrument does. Okay. This is called the coordinating measuring mission. Okay. This is an optical one. So which will measure the X, Y, Z position of the any component you place on that thing. So you can see. Okay. So Mukund will explain a little bit more on the CMM mission, how it does and what you can do it, and you can take automation of the program also you can do it.
Okay. So basically, I will give a brief work around for this machine. So if you can see, there we have put a PCB on the CMM glass, and we are seeing the images or the high resolution images of that PCB in our PC. So the work of the CMM machine is to get the coordinates for any point that it is pointing to. So if you can see here, we are seeing the current coordinates of the points. And this machine is the one that we use to do the quality control and quality assurance studies on our assembly procedures. So as Kameshwar mentioned, you can see the wire bonds made here. So the job of the wire bonder is
So one sec. So these three things are three little wires.
Yes.
And how big is this? Because you're looking at it through a microscope, right?
Yes.
So these wires are how thick?
So these are
The diameter is 25 micron.
So it's 1 mil wire. So this is 1 mil wire, which means 1 milli-inch or 25 microns. So this wire is 25 microns. There are three wires. They have been sort of connected from this to the center over here.
yes.
And what you're looking at is a microscope image of the actual
PCB.
PCB is sitting under the machine over there. But what you're looking at is effectively the microscope image of it on a screen. And they can control it and actually make these very, very accurate wires which are soldered at the right places.
Yes. And other uses of the CMM machine is we can do the geometrical studies also. Like say this is your this is some circle or some circular feature you want to study. Then I can use the CMM machine to get all the required parameter for that circle. For example,
So you can basically look at every part of the board in the machine.
yeah,
Is that
every
correct?
part of the board, and it has some contour extraction and feature detection mechanism that can help me find the circle and all the required features. For example, here I have traced a circle, and with just one click of a button, it will give me all the important features. Like it has given me the center of the circle and diameter, radius, and circularity, etc. So you can do the similar things for, let's say, a square, a rectangle, a arc, and all other things. So it's a very important machine for our job. We validate all our procedure via this machine.
So this is inspection machine.
Yes.
Okay.
And next we will go to the big gantry and come.
So this one, whatever the CMM I told, I will show the assembly. Before the assembly and during the assembly, after the assembly also, we use that CMM machine to measure all my parameters, particularly delta x, delta y, and the rotation. So this is one called is the aerotech gantry mission. It is a fully robotic, which will move in delta x, particularly x, y, z, and the rotation. It is a 4-axis system. 4-axis. It is a 4-axis meter, which can do. So here you can some of the jigs are there. We call the jigs. So for each, this is called sensor pickup jig. I will show you one of the video which just now I play. And this is the PCB jig. And these are the jigs used for the assembly of my module. So in the I will show you what is what. And it has three components as I told you. The base plate. Here which you can see the base plate. Okay. Base plate with double-sided tape is there. Right now there is a thing. So what we will do, the base plate will be placed here and hold with vacuum. And we will dispense the glue here, wherever this position. And we will remove the tape also, the double-sided tape. And it's kept ready for the placing of the sensor. So here this is showing the center. This is the fixture for aligning the sensor. You can see all the tiny holes and circles are there. So there, whatever the shown in the CMM. So we need to perform the bonding on each of this circle. Nine bonds on each circles. Okay, this and this thing, and then this will get placed. After that, we'll dispense the glue on the sensor. After placing that thing, then we'll place here one more picture given for some modification. This picture also similar to this one. this thing also by line here, particularly on the picture, and later we'll pick up. Here is one of the different everywhere the holes are there. So picking up is very difficult. We need to pick up in such a way that you will pick up this thing and place it on the sensor properly for going. So this is one of the module. This is one of the assembly module you can see here. All the base plate is here, and the sensor is here, and the PCB is here. This is one of the assembly module. So here most of our sensor is around 300 microns, the thickness. And here to operate this is one of the, we have some, that is an 8-inch module, what you are working. So we have some dummy, we received it, it's called the, on 6-inch. So which is having, everything, these are all called the readout chips. So which are all connected into these things, and these are some of the power supplies. And here also at the each location, we need to perform the wire bonding as shown here. That's what. So after this thing, I will already to assemble these things. What you need is fiducials. We have some fiducials here, and some of the fiducials are also here. So to align perfectly, we use these fiducials to align and pick up and properly. I will show you the real video how this fellow will pick up and play in a few minutes. And all this thing, it is connected to the my system through the industrial PC with the its controller. And the controllers are there. And along with that thing, we have some lot of DC power supplies and other vacuum connections are there, which you can see in the bottom. Lot of vacuum connections because everything is on and off as per requirement. Okay. So on all these things are connected to the lab view. And I'm just showing is now everything is ready. Now I'm just keeping this thing to start so that we can that start most. Okay, I will show you. Shall I start? Start. Now you have to go to the before this video. Now this fellow is coming and picking up the pickup tool for the sensor. That's what it does. First it pick up. So the vacuum will come and hold the pickup tool, which you can see here. It picks up and it lifts. And it try to move to the sensor where I wanted to pick up the sensor. Now it is trying to pick up the sensor and right.
There. Otherwise your sound won't go.
It will try to pick up the sensor and it lifts and it waits for one more command. So at this stage, what we need to do is we need to remove the tape. This is a prototype. I'm not showing really. So we need to remove the tape. And before that thing, I should give some enable. Just wait a minute. I will give the enable signal from here. So I enabled it. So now it's coming to place my sensor. It picked the sensor and place, and it is rotating because my channel number 1 is at certain location. So I need to place the channel number 1 at that location. This is how it plays. And this optimization of the height and everything we have done for the sensor. Now the placing of this thing is there. Normally after placing these things, we need to keep this one like for another 20 minutes so that the glue, whatever you place, it will be cured. And similarly, the tape will be there. The tape also will hold the sensor with the base plate also. That's what. So after this is the same procedure for the PCB also. Okay. This is the only one step we can show in this video. Yeah. That is a different setup for that thing, which you cannot show it now. Yeah. So after these things, as we have the automatic wire bonding mission. So I'm not. So this is the fully automated mode mission, and this thing was used for our belt to experiment to perform these things. And one of the each ladder for layer 4, we have total 10,000 wire bonds between the pitch adapter, the sensor, readout chips. So we need to perform so many wire bonds on these things. Yeah, that's it.
All right. So fantastic. So you are basically making very fine detector the complete module.
Yes.
Ready for deployment.
Yeah. To add this thing, one more thing, with the time, our production target, which is very high. So roughly within next 2 years, we are planning to make around 4,500 modules of similar to this one. That is the target for our this thing. So we are still optimizing a few of the parameters, and we are waiting for some of the components prototype, and we would like to make the initially the prototype. After that, we wanted to make the electrically working, and we'll make sure that starting to ending everything is working and fine and tested. We have the DAQ setup is also there to test this module. And once everything is starting ending, then we'll assemble all the modules, particularly the 4,500 modules here, and we'll send it to the sir. This is project format for the sir. So we'll all this thing will ship to sir. Yeah.
So this is a part of a very big international effort wherein probably thousands of people are involved.
Yes, so many. A lot of countries are involved.
Yeah, not like some small 4-5 group of people working together.
No. We are doing some tiny part, you can say, yeah.
Yeah. Right, great.
Thank you.
So shall we go over to Professor Mohanty?
Yeah.
Yes.
Okay.
Yeah. Can you hear me? Do you hear me from Mumbai?
I realized why we were not able to see it in the microscope with your camera. Because the brightness was very high. If you want, we can try that again. Or if Gagan is ready, we can ask Gagan to tell us something from CERN. So, Gagan, are you ready? In which case, we will just spotlight your video. I can do that. Here. Remove spotlight and yeah. Okay. Just a second, Gagan. Please wait. Spotlight for everyone. Okay, Gagan, your video is now spotlighted, and we are now going to Gagan at CERN. And yes, go ahead.
Yeah, I hope you can hear me and see me. So there, there's 2-3 questions which were raised during the discussion and also in the YouTube. I thought I will just take a minute or two to explain those things. First of all, this international collaboration are really kind of large-scale collaboration. There's a question raised, how big is the collaboration? For example, the CMS collaboration is 4,000 people, about 4,000 to 5,000 people. And, this ethical thing that Kamesh said about 30,000 module will be built is distributed across 6 sort of institution around world, 3 in the US and 3 in Asia, 1 in China, 1 in Taiwan, and 1 in India. We are doing in TIFR. So each one roughly taking 4,000 to 5,000 modules. There was another question which was raised in YouTube about can we detect neutral particle? Kamesh said we mostly use the charge particle, we detect charge particle. The question was, can we detect neutral particles such as neutrino? The answer is yes, we can, but indirectly. What we have in the calorimeter, we have the silicon detector. Before that, we have some kind of copper tungsten or some kind of, a large jade material. So when the neutral particle come, they interact with this, before reaching silicon, they interact with this material, and they detect charge particle. Then once you have charge particle, they interact with the silicon through ionization, and that is how we detect. So it's an indirect process. So similar, we can detect photon, we can detect neutron, we can detect neutrino, so on and so forth. Of course, it's a different question that neutrino interact very, very feebly, right? So that's a different matter that we really don't see neutrino in the CMS detector directly, right? So I think these are the 2-3 questions I wanted to answer. And I don't know if there is any more question, or otherwise we'll just go back to Mumbai. I'm done.
Before we go back, Gagan, behind you, I can see a big TV screen that is displaying all kinds of interesting things.
So
Yeah,
can you tell us a
absolutely.
little bit about what is it that's
Right.
behind you? Yes, I mean,
Yeah,
now
yeah.
there is a
So
picture of I think the detector, the cross section on the right top corner, and there are
yes.
lots of different. So what in every room can you monitor what is happening in the detector? Will you tell us a little bit about how it is?
Absolutely. Thank you, Arnav, for asking that question. So this is in fact, we are sitting in this called building 40, which is kind of the main building of so-called CMS and Atlas experiment. India is participating in CMS experiment. So what you see in this big display here, when these proton-proton collisions are happening and these particles are coming out of it, we see that different sub-detectors. So CMS detector is not just one detector. It has made up of several detectors. There is a tracking detector, there is a calorimeter of two kind, and then the muon detector. So you can see at the different detector how these particles are giving signal. For example, you can see there is this sort of you're taking you're taking that slice of the detector and how this particle, you see there is a signal coming, right? Sometimes you see the signal inside the calorimeter. Sometimes you see there is a track as a straight line or is a curved track. So that's what we see. And you see how the detectors are, is the detector is operating well or not. So we can detect even from here, right? So this is a display of the actual thing which is happening inside the detector in a sense.
So right now
Okay.
the machine is running. So the
Yes,
particles are colliding with each other right now. And
absolutely,
this happens
absolutely.
24/7, or it happens only at certain times, or how does it work?
Right. So the detector, so the throughout the year there is certain period during which the data taking takes over. For example, the peak of winter, between December to January we have winter shutdown because the power bill, the electricity bill is quite high, and but anyway, and there is also summer shutdown for some time. But otherwise, once the experiment is running, it is 24/7. So we have people like us, student, postdoc, faculty, engineer, they take experimental shift. Once the data taking is gone, undergoing, we can't sleep. Like, for that particular, the whole 24 hour is divided into 3 shift of 8 hour. So people take shift. So it is 24/7 once the data taking is ongoing.
Great. And the detectors that have been made in your lab are also in that experiment, or are they going to
Absolutely.
be there?
So the current detector, what Kamesh just explained about ethical, they will be put into use during the so-called high luminosity phase, which will be starting from 2029, 2030. However, in the current detector, yeah, okay, I was involved as a student. So this is the time is called outer hadron calorimeter. So TIFR group built the so-called one part of the calorimeter, the outer hadron calorimeter. That time I was a PhD student like Lokesh or Mukund, and I was involved in the quality monitoring test of those detectors a long time ago. And so that detector is right now taking data. However, sort of they are getting old over the time. And when high luminosity LSC phase will come, we'll completely revamp the calorimeter on the end cap. So the detector is just like a cylinder, as you can see. So the core part, we call it barrel, and these two part we call it end cap, right? So the end cap calorimeter will be completely replaced by this high granularity calorimeter. So what we are building for future, and we had built it in the past, the detector.
Great. That's fantastic. Fantastic to know that the work our students will do now will actually be used in the detector in 2028 or 29, whenever the high luminosity runs are done. That is fantastic. Now, anything else from you, or should we move back to the lab over here?
Please, I think I'm done unless there's a questions. Yeah, so we go back to the lab.
Let me just. Okay, so we have Ulhas's mobile over here, and now we figured out why we couldn't see these things very easily. So maybe what I will do is I will show you the detectors under the microscope again. So just remember, this is a prototype detector. This is a prototype detector. This has pretty large tracks, as you can see. But remember, what you're seeing are actually collections of tracks. In each one of these lines that you're seeing are many, many, many tracks. Okay, so I'm going to try and show you this through the microscope right now. So let's put it out here under the microscope over here. And can you get your can you get your camera over this and give it to me, and I'll take care of it. There we go. Oops. Okay. Okay, can we reduce the brightness? That's what we need to do. We just need to reduce the brightness and everything will be.
Turn off this light.
No. The brightness of
This minus sign here.
the minus sign. Can you hit the minus sign? Yeah. Okay, there you can see a little bit of it, but oops. Can you keep this display on for some reason? Okay, that's
software issue.
yeah. There. Only we can focus this. Wait. There we go. One sec. Okay, now. Hold it steady. Yeah. Can you zoom in a bit? Now you'll see the tracks. Zoom. No, not there. Zoom on the microscope. It's on the right side. Or both sides. Yeah. Okay. Good. Great. There you see the tracks. It's very difficult. This is meant for your eyes, but if you can see these fine lines on the track, you can zoom in more. Go ahead. Yeah. Go ahead. There you see the lines. Those are your strip detectors. Those are the strips. Exactly. Those are the individual strips. That is what we were trying to show you earlier. These are the individual strips of the strip detector. Okay. Can you move it to the pad? Can you move the wafer so you can see the pad? Move it gently. Yeah. Move it outside. There we can. Yeah. There we are. You see these two little things you see? That's where the wire connections will be made to take the signal to the outside world. Now, this was a very big detector. There's another detector. You can put the other wafer. Yeah. That you see that this has got much finer lines on this. In fact, you can't even see the lines. Okay, this is now vertical. Yeah, but you can see that the lines are much finer on this one. They're much finer. The lines are much finer here, right? So this is a different kind of detector. Yeah, you can go out a bit now. Zoom out a bit so that we can see the whole thing. Yeah, you can see all the lines. See the very fine lines. These are all your detectors, and those are the pads. And these are the lines over here. Okay, and there are some little marks outside where are test structures. We can go to those test structures which have letters and all on them. Yeah, the ones at the corner. Go ahead. Yeah, the blue pad, exactly. And now you can zoom in. You can see some writing out here as well. Yeah, so all the details, this is which layer it is, etc. These are all test structures that tell you exactly what is happening at this detector. Okay, sorry, this is the best I can do holding the mobile in my hand, which is connected to the Zoom. But I hope you got an idea that this chip, and you didn't see this chip so far. Can you just get the screen on? But this is a different chip. This had the very fine lines on it here. You can see the difference. These are very fine. And what you were looking at with the letters were things at the side, which were these little things below the. Yeah, you can see both of these. There are two detectors now. You can see them.
Can I add one?
Yeah, please go ahead. Go ahead.
This is we have 11 sets are there. So which are different width and pitch. And this file has only one set. And each this is 1024 strips are there with 50 micron is the width and 75 micron is the pitch. That is the difference between these.
Yeah, so 1024 stripes in this little detector.
Yeah,
strips. Okay, so are there any questions here? Take back the camera. You can ask. So, Kamesh, Mukund, Lokesh, they can answer questions.
Yeah.
So let's see. Okay, so Arush has a bunch of questions over here. I hope you can still hear me. Arush is asking, are the detector designs specialized for specific types of particles, or do most use similar designs? So if you're detecting electrons, protons, whatever, do you have different detector designs, or are they all the same?
So for we take into account which particles we have to detect. For example, the CMS is a what we call a general purpose detector. So it can detect all the particles coming into it. As Gagan sir said, some particles like neutrinos, they are hard to detect, but they can be detected indirectly. But for Bell, something like Bell experiment, So the B in Bell stands for beauty or the bottom top. So the Bell experiment is more designed towards detecting the Bell mesons or B meson.
Also in CERN?
No, Bell experiment is a Japanese collaboration, and CMS CERN has 4 experiments right now: the CMS, Atlas, Alice, and LHCb. So similar to Bell, LHCb does the B meson study, and CMS Atlas are general purpose detectors, so they detect all the particles, and Alice is more geared towards the heavy ion collision. So instead of proton-proton collision, Alice looks into the lead collisions. So
some detectors are particle specific and
Yeah.
some are general purpose.
yeah,
Like I would like to add one thing that like CMS is a detector. It is made up of sub-detectors like calorimeters. So there are two different types of calorimeters. One is electromagnetic and another is hadronic. So electromagnetic calorimeters, they are meant to measure the energy for electrons and photons, while hadronic calorimeters are meant to measure the hadrons. So
Okay. There's another question. What makes a detector resilient to high voltage or luminosity? I don't understand. I mean, I suppose they mean that.
What is it?
What makes it resilient to high voltage or luminosity? I mean, will all these particles going through the detector not damage the detector?
It will.
it will, yeah.
So the
Can I-
reason, particularly whatever the detectors, whatever we test, normally you should, normally these detectors will keep it for 10 years because every now and then we cannot remove and put back. Okay. So before putting any detectors, we'll test the detectors to such a way that the crystal structure will be able to withstand these 10 years of the radiation intensity. So we have to design such a way that the detector will withstand that thing. So that's why all these things will be chosen, the detector specification also as per this thing.
I want to add one.
Yeah, go ahead.
Yeah, so I just wanted to
So-
add two small points. First question, Mukund has already addressed well. Specific to the silicon detector, indeed there are special design. When you are using silicon detector for tracker or vortexing detector that Kamesh said for Bell 2, we use the strip detector because you are tracking the trajectory of the charge particle. When we are using it for a calorimeter, we do not use the strip, we use a pad detector because here the particle are going and sort of there is energy we are kind of detecting, and as the particle propagate, they generate a shower. So therefore, strip detector will not work there. We have a pad detector, each cell measuring some part of energy. So indeed, there is a specialized design for each detector depending on for what purpose you are using tracking or calorimetry. That is an additional thing what I wanted to add to Mukund. On the about of the luminosity, so as you know that why do we age? Like there is some ambient condition, so the detector also age over the time. And as Kamesh said, first of all, the silicon detector we want to make them very very thin. Where you have more radiation damage, we want to make them thin and thin. What happens? So therefore, when the particle pass through this detector, they deposit minute energy, right? So minute energy means the detector will be less, they will be more resilient against the damage. However, when you operate for several years, there will be some internal damage. So in order to mitigate that, we run this detector at lower and lower temperature. So this so-called the leakage current increases as the detector becomes more and more old, age. So in order to mitigate that, we operate them at a very low temperature, right? So that is how we do, and that's why what Kamesh was saying, that the the breakdown voltage should be as high as possible, because you can operate at a higher and higher operation voltage, right? So that is why the the breakdown voltage has to be large. So as the leakage current increases, we have to operate them at lower temperature and higher higher operation voltage. So these are the two things. So I wanted to say. Back to you, Mumbai.
Okay, so Gagan, I wanted to ask you one more thing in your explanation. So I understood that there are two types of detectors. There are some detectors which are optimized to detect the total energy, and things like the strip detectors are detecting location. So you have
Correct.
different detectors that can detect the location of the particle and hence the trajectory, and there are other detectors which are determining the energy that is deposited.
Right.
Is that right? So there are many
Absolutely.
different types of detectors that are there in any particle physics collider experiment.
Absolutely.
Gagan, there are a few more questions on the chat. Maybe
Yeah, we
it's
can
best
take
you
it
can
up.
answer them. The first
Yeah,
one, of course,
okay.
the most interesting one is, what is the price of the detector?
The price of the detector, it is quite, I mean, just roughly speaking, one detector that Kamesh was showing, that strip detector, roughly 3 to 4 lakh, let's say, something like that. So they are very expensive. And so that is why it is very important to realize since this is very expensive detector, we do lots of mechanical mock-up before using the actual silicon detector. We do lots of mechanical exercise. We do many things, mock-up exercise, so that when we deal with actual detector, we are really not wasting them, right? So that is the thing. But of course, there will be we have to build in some contingency into our into plan or program, right? But yeah, they are expensive detector.
Well, 3 to 4 lakhs was only the raw wafer, right? By
For
the time
one,
you actually put
correct.
it on the PCB and fabricate the final detector that is going to go inside the collider, it's probably gone up to 30 to 40 lakhs or maybe even more.
Correct. 30 to 40 lakh,
okay.
but multiply by 30,000, right? So you have to see, I mean, that's the price of the detector, but there are the human resource involved making it, sending it to different place, so if you build in the entire thing, that is even more expensive, right? I was just saying the one unit takes this, but of course, when you build the one module, you are talking of 10 times more expensive.
Okay, so the other question was about blind spots.
Right.
Depending on the pitch and the spacing, are there blind spots in a detector? Is again somebody has asked, which is I think a good question.
Yeah, so the question, I can take it up. So basically the question is, you have the pitch and the resolution is divided by square root of 2. So what we do, actually, we can improve it better. What we do, as Kamesh was showing, that it is a strip detector, and each of the strip detector are measured. Each of the individual detector behave like one detector, let's say, each strip detector. But sometimes to improve it more than the square root of 2, what we do, between two readout strip, we introduce so-called floating strip. So if you go back to your electrostatic, the charge division, so there is a capacitive charge division. So we can get the signal to noise ratio even, the resolution even better than square root of 2, right? So now you say, well, I want to do even better and better. So you have to reduce your strip pitch, right? I mean, if you make the strip pitch of 100 micron, then you get to some resolution. If I make it 10 micron, right? So I'll do even better. So yes, so the resolution, you can't make it infinitely precise. There will be some finite resolution, but we improve it as much as possible.
Okay, and finally, there seems to be a question from Jas Chaudhary about whether these detectors are useful only for high energy physics or they have other applications in medicine or
Absolutely.
what is it? Biomedical applications, etc.
Absolutely.
So are these detectors used in other places?
Absolutely. So these silicon detector are very much used in medical application, particularly the so-called mammography. So for the cancer, the breast cancer, like sort of in order to see the tissue, like sort of. So there we want to see, like you inject some the so-called high energy particle radiation, whatever you do, and then you want to see the effect, and that is where the silicon detector, because it has got a very finer position resolution. You can track down that how the interaction between the tissue, the live tissue, and this particle, that whatever the therapy you are doing. So it is used, and this is thanks to the excellent position resolution. So they are used in medical.
So basically, the work that we do in fundamental physics also has often offshoots into different areas that help humanity, overall,
Absolutely.
which we often do not think about when we are working on it for the pure physics part of it, but maybe after a few years it gets used in other applications as well.
Absolutely.
Okay.
That is the
So
thing. And
are
in
there
fact, silicon
any
detector
other
are
questions
currently
that
used
anyone
for the.
has? Let's check.
There is one question, what is the Abhinav Chaudhary, what is the impact of long-term radiation on silicon detector? So yes, so that is the question was temporarily answered, sort of partially answered when I talked about this high radiation, high luminosity. So basically the silicon has got two kind of damage. One is called surface damage. Another is one what we call the lattice structure being changed. So mostly we are more worried for the surface damage, and we take necessary precaution and things like we have to, since the leakage current increases, we operate it at a much lower temperature, and also we increase the operating voltage, and the bulk damage at certain stage, in fact, when you have PN junction diode, it will completely become the type inversion. So, but we have way how to go around it, right? But of course, we cannot use the detector for infinite amount of time. At some stage, they will die, and that's what is happening for this current detector. At some stage, they will completely be revamped. The silicon strip detector for the CMS tracker, they will be no more useful, at least for the particle detection, and that's why we'll have a new tracker. But yes, there is a impact, and we take necessary precaution to mitigate the impact to some level. At some point, they will have to be replaced. Yeah, I think that was the question I can see on.
Okay, so on that note, let us thank everyone in the lab here for really taking us around a tour of exactly how these silicon strip detectors are used and put inside for these high energy physics experiments. And a special thanks to Gagan for waking up early and joining us from CERN, live from CERN in Geneva. And before we wrap up, just a reminder that a week from now is going to be the first Sunday of July, where we will be back to our regular sessions at Prithvi Theatre. We're going to have Amol Dikhe speak about probability in the quantum world. And this has come some very interesting examples. For example, from Sholay, if Gabbar was shooting bullets, but they were quantum bullets, how would they be and how different would they be? So that's going to be another fun session. Do join us, either in person, preferably. There's also chai. There's no chai if you're watching us online. Or you can even join in online. Keep tuning into Chai and Why. If you have more questions, feel free to send us an email. Our email address is outreach, outreach, at tifr.res.in. And we will be happy to guide you to, send your question to the right person and make sure you get a reply. I hope you enjoyed our session. Thanks once again. Thanks, Kamesh. Thanks, Lokesh. Thanks, Mukund. Thank you very much. And thanks to Ullas. He's been behind the camera trying to hold a mobile phone. It's not that easy. So thank you all and see you later. Bye for now.
Bye-bye.
Bye.